Hi, good afternoon, everyone. So here we are in lab number 4 of this series, looking through the different calculations for the different labs. So here for this lab now, we have our moments. And we can see in the calculations, all we got to do is find the gradient, equation derivation, and mass of the ruler calculation. So something that shouldn't be too challenging. Anyways, so let's get right into it. As we can see, like a lot of these things are equating the gonna give us a formula, and we got to take the equation from the graph and then equate it to the formula. Now in this case we don't really fully have that, so let's see what is going on here. So let me see the gradient calculation. So we should have a graph. That's the first place to always start. All right, let me start with our graph. Bam. All right. And what is plot on the x-axis now? Well, on the y, sorry, is D1 versus D2. D1 versus D2. All right. Cool. And we should be getting a graph looking like this. Bam. Not too bad. So this graph is, D1 is proportional to D2. Right? A straight line graph, right? Y equals ms plus c, all it proportional, right? All right. So we go through this a little bit more slowly. Yeah, we gotta go through this a little more slowly. So now on the physics half of this, we gotta use some real physics. So this is our mathematics half. No, this is our physics half. All right. So we have this setup. We have D1 and we have D2. Observe these things. These are important. And it says, using the principle of moments, derive some equation. So this is our setup. Basically, we have the meter rule. We have a fulcrum placed not in the center. And we have D1 is, we have basically a mass over here. And then the center of gravity pulling it down. All right. Bam. And we need to come up with something here. All right. So the distance between our mass and our fulcrum is D1. So the distance in between here is D1, and then the distance between our center of gravity and the fulcrum. All right, between the weight to the ruler, where the weight to the ruler is acting, and the fulcrum is the number 2. All right. And we basically need to come up with this equation, right? With the gradient. Now, the gradient, what I want us to keep in mind is the gradient is, all right, the gradient is going to be the change in D1 over the change in D2. All right, so we're going to need to have a D1 over D2. All right, sure, whatever. Let's get cracking. So the principle of moments. If you remember the principle of moments, don't tell me you ain't know what that is. The principle of moments should be, all right. So you're right, using principle of moments. All right, using principle of moments. If you write POM, I know what POM stand for, right? If I'm marking it, I know. So tell me what's POM. Using principle of moments, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moments about that same point. Cool. So let's look at this, the mass, right? This is the force that the mass itself, the mass holder. So I'm gonna use M. I'm gonna use M for mass holder. All right. So the mass and the mass holder had exerted some forces down on our ruler, and when it exert down, let's see if this were to rotate, what direction would it rotate? It will rotate going around the pivot like this, and that direction going around would be anti-clockwise. So I know that this mass, the mass holder, is going to create an anti-clockwise moment. All right, TM. All right, TM. The moment created from the masses is going to be on the anti-clockwise side. What about the way to the ruler? The way to the ruler is going to be coming down. Bam. All this is going to be on the clockwise side. So the moment created by the ruler, um, I will just put weight, right? This is the weight to the ruler. Is going to be on the clockwise side. All right, so these two moments are going to be equal if we are in equilibrium, right? Because at equilibrium, the moments are going to be equal. Bam. So now we need to find out, we need to express these moments in terms of forces and distances. Remember what's the equation for a moment? Equation for a moment, T equals force multiplied by perpendicular distance. Yeah. So that's all we need. So what is going to be T? Let me answer. Sorry, what's F? All right. So what's the force? So the force now of the mass. All right. So we have force of the mass multiplied by the distance. And what distance is that? D1. Okay, cool. Now, what about the weight to the ruler? So we have the force. Well, this moment by the weight to the ruler. So we have the force of the weight, or the force. The weight is a force, right? So we have the force, or the weight multiplied by the distance, and this is D2. All right, cool. So we're going good. Now, what about this F of this small m, right? This small m is the mass holder. So this, if we want to get this force, what we need to do is take the masses of the mass holder plus the masses, right? Get all those masses, multiply it by the gravitational field strength, right? Bam mg, right? To get it into a weight form. All right, remember weight, the equation for weight equals mass multiplied by g, and weight is a force. So if you want force, force equals mg. So you take your mass, you multiply by the gravitational field strength, which is 10 at this level, and bam, you get numbers in forces. So you have your force, mass, the mass and all these small mass holders multiplied by g, multiplied by d1. And then this is the force of the weight of the ruler. Perhaps, yeah. Let me just keep this with W. I mean, I've used R before. All right, I've used R before, so we know we're talking about the ruler here. So what's the force of the ruler? It's going to be the weight to the ruler, which is going to be the mass of the ruler. Woo! And get a little complicated with these M's and things. So let me have this. So mass of the ruler multiplied by all right, mass of the ruler multiplied by g. All right, so let me rewrite this just so that it looks a little bit more aesthetically pleasing. All right, multiplied by d2. And this is going to be mass of, we can call this h, or the mass holder plus the masses. Sure. So you want to make that h then, just to be consistent. Yeah. Um, yeah, we could do that. So for the holder, yeah. All right, for the holder, the force of the holder. Yeah, I think this works pretty nice. All right, and we need to find m, and this big M here, so now is the mass of the meter rule. So if we're looking at this equation here, we need to rewrite this equation. We're looking for the equation mass of the meter rule, so we're looking for our mass in meter rule, which is mr, meter rule mass, equals gradient multiplied by m, and that small m now is the mass placed on the meter rule, which is our mass holder. All right, so we're looking for something looking like this. And wait, we're getting kind of close. Now those g's, we can multiply by 1 over g, or move a g over the other side. It's going to cancel out. So we get mr d2 and mh, right, for the mass holder, a mass of the ruler, and mass of the holder. So we get mrd2 equals mhdone. All right, so we almost there now. And the gradient is going to be, the gradient we say is, d, mm, 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 mhm. All right. All right. This gradient is supposed to be d1 over d thing. Oh, yeah, everything working out. Sorry. So now this gradient is going to be d1 over d2, right? So let's move d2 over. We're making this mr the subject. So the mass of the meter rule, all right, equals the mass of this holder d1 over d2. And we're like, oh no, this doesn't look the shape how we need it to look. But all we need to do is use our mathematical tools of understanding how fractions work. And you realize that it is already the same thing. Right? So we got MR. And what I'm going to do, since we have a strong understanding of math, bam, separate them two out. And then it's like using another strong understanding of math, we just rewrite it into this form, d1 over d2 multiplied by mh. Bam. And then we could say using using conventions given, conventions 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 conventions. I have no idea why I didn't spell it properly here, but using conventions given, all right, we know that mr equals big M, and then mh equals small m. So we have big M equals d1 over d2 multiplied by small m. And then we have big M equals gradient multiplied by M as required. Bam. And that is it. That is your derivation for this. So this one was definitely a little bit more challenging. This one is definitely a little bit more challenging. But all we needed and truly to do is take the principle of moments and then come down the road. You could actually shorten this. You could shorten up this, but I decided to write it out in full because, there'll be a few who need to see it in full. All right, so then that will be the mass of the equation derivation, and then the mass of the meter rule. Well, you got the gradient, you got your masses that you recorded, the mass holder plus the masses used. That's this small m, bam, 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 multiplied by the gradient, bam, get a big M, and that is going to be a mass of the ruler. Putting your sources, precautions, sources of error, and a conclusion. All right, guys. So that wraps this video up. I'll see you guys in the next one. Later.